workshop. My name is Robert. This video is part 5 in the series on the gear cutting attachment I made for my Elliott 10M shaper. In this part I will be using the setup from the previous video to cut a 14 tooth 20 dp 30 degree right hand helical gear in SAE 660 bronze. I will then reconfigure the machine and cut an 11 tooth 20 dp 30 degree left hand helical gear in EN8 steel. I'll then run the two together to prove that they work. Thanks for watching, let's get started. But first, before we actually get to cutting, we've got to set up the dividing head. And as I'm intending to cut a 14 tooth gear on this blank and an 11 tooth gear on the next blank, we need, for this gear, we need a hole pattern here which will enable us to do that. So this is how I determine which hole circle we're going to need. I don't rely on tables, I just do it from simple rules. We have a 14 tooth gear. The dividing head we have requires 40 turns of the handle for one rotation of the spindle. Therefore, to index from one tooth to the next, we need 40 divided by 14 turns of the indexing arm. Now 40 over 14, if we remove the whole part, there's 2 turns plus 12 14ths. Reducing that down, that's 2 6/7 in its basic form. So we don't have a 7 tooth plate, we don't have a 14 tooth plate, but we do have a 49 hole circle in the plate. So if we multiply that by 7 and we multiply the top by 7, we need 2 turns and 42 holes of a 49 hole circle plate in the plate. And that's what we use. Simple as that. If we were going to replate it for the 11 tooth gear, we would need 40 over 11, which equals 3 hole turns and 7 11ths. Now we can't reduce that fraction any further, that's fine. We don't have an 11 hole circle, we need something which has a factor of 11 in it. We do have a 33 hole, so if you multiply top and bottom of the fraction by 3, we need 3 and 21 33rds. So that's 3 hole turns and 21 holes of a 33 hole circle in the plate. That's how we do it. Simple. So this is the plate that we need. It has a 49 tooth circle there, or hole circle, and a 33. So this will do the 14 and this will do the 11. So now this goes on here, line up the holes. Fiddle around and get the screws in. Drop the Allen key. Drop another one. These do not need to be stupidly tight. They're not really taking very much force. And as they're these countersunk headed ones, if they're done up too tight, they will only be more difficult to undo, and then the little hex heads will give way and I'll be left looking for some new ones. So that now goes back on there. I'll dig out the sector arms. And 2. Pop the clip on. Rotate the arms. So this little screw can go in. And these are ready for setting up. Okay, so now we determine where to place the sector arms. So we're going to use the 49 hole circle. So we're going to start off in this one here. We then need to come 42 holes past this one, so we don't count that one. Then we'll have to go to that position there. So that's where we'll tighten it up. Normally you do this with the indexing arm on, but because it's off, it's actually easier to do it while it's off, so I've taken full advantage of that. And there we are. We will move from there, go all the way around the outside to there. We will then advance this like that, and then the next time we'll have to go all the way around to here, not forgetting to make the 2 hole turns as well. It's worth taking a bit of care over this, because if you get it wrong, the results are, shall we say, disappointing. When I was testing out the spur gear fixture at one point, I just wanted to prove that it would cut the undercut properly and create a gear. This has got far too few teeth for the size of gear, but just purely as an experiment, I cut this one in aluminium, and this, as you can see, is a 10-tooth gear. Now, if you get the indexing wrong, what you end up with is something that looks much more like this. As you can see, this is a 9.5 tooth gear. It doesn't work. Okay, so if you've sat through all this video so far, now we've finally come to the point that you've been waiting for. We're going to cut the gear. So I've blued up the blank, I've checked all the nuts and bolts around everything to make sure everything's tight. I've oiled all the gears, everything that needs a touch of oil, and I'm ready to set it going, feed the tool slide down until it scratches on the workpiece. I then need a depth of 1/108 thou from there. So let's begin. You've got pretty much the view that I've got from up here. In fact, if truth be known, you're slightly closer. Here we go, we are just scratching the surface there. I'm going to take a first cut of, say, 50 thou. This is bronze, not aluminium. It's a nice easy machining bronze, C660. So firstly, let's wind everything back to about here. Should be a good starting point. Let's put on 50 thou of cut. Now at this point you're probably thinking, that doesn't look right. And I'm stood here thinking, that doesn't look right. Back to the drawing board, let's work out what's gone wrong. Well, that didn't take very long to work out. We need a ratio of 5598, and what I've effectively done is I've put the 45 gear on the dividing head, whereas it should have the 24. So I've got the gear train backwards. So it's feeding far too fast. Whoops. Right, we're ready to go again. We have the replacement gear blank in there. Everything is set up as it should be. I've had my trial practice on the one that I stuffed up. So let's get the shaper moving and touch off and then start cutting the tooth. We're going to go 50th hour time. So we'll take 50 thou for the first pass around. Then I'll probably take about 30, and then we'll finish off with or maybe do 40, and then we'll finish off with a much lighter cut for the final pass. Right, that should be in about the right place to start. It's blued up so you can see it cutting, so you can see what it's doing. Okay, this is failure number 2. Whilst I was messing around with another camera, let me go handheld and show you what's happened. The gear down here, the helical is disconnected. And so for the third time of asking, let's touch off and put some cut on. There we go, just touched off. Here we go, cut's just starting. Clear, and off we go again. Right, time to set up for the final pass. Now, the depth for the gear should be 108. I'm going to give it another 2 thou to give it a little bit of clearance for backlash so that it will run at the expected spacing. Last but one tooth, just this one, the next one, then out it comes, bit of deburring, clean it up, and we'll have a look at it on the bench. There we are, all done. Okay, so here we go. Pop that in there. There it is. That fits in there. Don't know why I put my finger underneath expecting it to drop out the bottom. That would have been going some. There we are. If it will focus. Now to cut the next gear, this is the gear blank I'm going to use. It's going to be a 20 dp gear, the same as the previous one. This one is a little bit smaller, hence I've not put it on an arbor. It's actually part of a spindle. This one will be 11 teeth. It'll be 30-degree helical, just like the last one, but I'm going to make this one a left hand, which means that they will then mesh together with parallel axles. So the first thing to do is going to be to disconnect the drive shaft down here. So. I'm going to slide off the banjo. I'm going to remove the dividing head so that I can dial in the table accurately to 30 degrees at the other angle. We're all set up. I've got everything down as low as I can. There's not enough room underneath the tool slide here to get my finger in. So this is sort of basically choked up as far as I can. I've got as little tool stick out as I can. I have the tool hanging right over the left hand side. As it's a left hand gear, if I bring it back on centre, the whole table will move so far to the right to do the cut that you run out of stroke basically on the table. The table will crash into the gears. So here we have the new gear train set up. This time I've verified it on a blank to make sure that it is cutting correctly. It has to be, this big gear has to be angled right over here as far as possible to keep the angle on this universal joint as low as possible. Otherwise it's not very smooth, it doesn't work very well. I mean, these things go to 45 degrees theoretically, but they don't work very well once you get anywhere close to that. But it's already all set up. The indexing is all set up and ready to go. So let's cut the gear. clutch off. A little bit heavier than I wanted, but that'll do. Bring it back. Put 25 thou on. Lock the tool slide. And off we go. Fourth pass. I'm going to treat it slightly more gently this time. We're going for 20 thou. Hopefully it will cut that okay, and then that will leave a 15 thou pass to finish. So I'm going to attempt to measure the distance between the two shaft centres when these gears run nicely. If you get them too close together, they grind. If they're too far apart, that's difficult to tell because there'll just be a lot more backlash. I'm going to use a technique that I borrowed from another channel, from Tom's Rabbit Hole. If you're not familiar with that channel, I'll put a link in the description. But if you're into gears, Tom has a homemade hobbing machine that he's been building, and there's a lot of interesting content on there, so well worth a watch. Anyway, thank you, Tom. This is his technique, and we'll attempt to use it to measure these two gears. In the vise of the mill, I have a stub shaft. I have a DTI which I'm rotating around the stub shaft, and it's indicating to me that the spindle is now concentric with the axis of this stub shaft. I have a DRO on the mill which I'm going to use to measure the position of this stub shaft now relative to the spindle. So this has been zeroed out. I've zeroed the DRO. I'm going to mount the little bronze gear on this stub shaft. It will be free to rotate. I will mount the steel gear in the spindle. I can offset the spindle, or offset the stub shaft relative to the spindle. Raise this, bring the two into mesh, and then we can wind the spacing to the point where the gears start to grind. Then we can back off until the point where they sound good. At that point, we'll have a reading on the DRO that tells us what the spacing between the two shafts are. We can then compare that with the theory saying it should be ideally half of the sum of the two pitch circle diameters. So let's get to it. So now we'll remove the DTI, place this little bronze gear on the stub shaft, rotates freely, put a washer and a bolt. This will keep it captive. As these are helical gears, there is axial thrust on them, up or down depending on which way they're going. That's now still free to rotate. I've got the 11-tooth steel gear secured in a collet, which will then nip up tight. Let off the emergency stop. DRO is reading 0. We will now back the spindles away from each other. I will now raise the knee until the two gears are at the same height, like that, and then bring them slowly together and bring them into mesh. So now they're in mesh, and if I operate the spindle, they rotate very nicely. I'll bring the two gears closer and closer together until they start to grind. Then I'll back off until they run as quietly as they're going to. And at that point, we can measure the separation on the y-axis here. That'll be the separation between the two spindle axes. We can then compare that with the ideal. Can you hear the grinding noise? Somewhere around there? They sound reasonably good. So we have a figure of 721 thousandths. So zoom right in this is the pair of gears at the spacing we've just measured, and there's just a tiny little bit of backlash on it, which is pretty much how you'd set up your change gears in your lathe. So this is the spreadsheet printout for the 14 tooth 30 degree gear, and it tells us that the gear pitch diameter is 0.808. The same spreadsheet printout but for the 11 tooth gear tells us that the gear pitch diameter is 0.635. So if we take those two figures and do 0.808 plus 0.635, we get 1.443 inches. Divide that by 2 for the spacing. So this is the sum of the pitch diameters. What we actually want is the sum of the pitch radii. So if we halve this value here, we'll get 0.7215, which agrees very nicely with the measurement on the mill. So it looks like the gears have come out on size with just a nice little bit of backlash. So they would run in a system that had been designed for these gears with a fixed spacing between them very nicely. Well, that concludes a series of videos on the gear cutting attachment. I hope you found it useful or interesting. Thanks very much for watching.